morning, everybody. I'm very proud to be in front of you to share some results about work in progress about ammonia liquid spray. So, as explained Christine, ammonia is a new carbon-free fuel, can be very interesting. So, and as explained Christine and Pierre yesterday, it's possible to use ammonia in the engine with a direct injection. So, the first step in the engine is atomization and vaporization. So, it's why it's very important to have a new knowledge about this subject and to work step by step. First, understand very well the atomization processes for ammonia with one ammonia spray. Secondly, understand the spray infection for multi-oil nozzle and mixing, and after to understand the impact on injection strategy on the combustion. Today, I'm focused on the first step about atomization processes for one ammonia spray and some results about the spray interaction for multi-oil nozzle. So the properties of ammonia are very different than gasoline, and there are two big differences. One is for the latent heat vaporization, and the other is for the vapor pressure. These two properties are very high compared than gasoline. So the ammonia stored in the tank under high pressure is liquid, and the condition of injection inside the engine, as shown Pierre, is for intake pressure about 1 bar and intake temperature about 80 degrees. So the vapor pressure is the back pressure is lower than vapor pressure than ammonia. So the processes of atomization are completely different than gasoline, and we can observe some flashballing effect in the nozzle or outside the nozzle. When the static pressure, the local test pressure inside the nozzle is lower than vapor pressure, depending on the local temperature, some bubbles are created, and this creation of bubble change the local temperature and the local static pressure, and to change this modification can change the bubble gas. So we can observe 3 stages of flashballing: nucleation, bubble gas, and atomization. I'm focused to describe this type of atomization. We can work with different dimensionless numbers. I'm focused on 2, the dimensionless of free energy per hour, C, defined by Lamana. This number describes the possibility of a bubble to grow. And the second dimensionless number is Jacob number to compare the sensible heat and the latent heat. And with this dimensionless number, it's possible to define different criteria with Kitleri or Kitamura criteria or Lamana criteria. And for different value of this number, we can observe 3 modes of atomization process. Full flashing, so the bubbles are completely filled the nozzle. For high Jacob number or very low C number. Transition zone, when there are some bubble onset in the nozzle, and for lower Jacob number or lower and very high C number, the atomization is dominated by mechanical breakup or external flashing. How is possible to observe the different type of atomization? Between mechanical breakup and transition, the flow rate decrease, the spray angle increase, and the droplet sizing decrease too. During the transition mode, the flow rate decrease, and the spray angle increase, and we observe that the droplet sizing decrease again. And when the full flashing arrived, there was some stabilization of spray angle and the stabilization of droplet sizing. So in parallel is for one spray, and in parallel for multi-spray, the spray can collapse during transition of full flashing mode. So the question is, do you observe the same behavior with ammonia? So we try to explore this matrix versus dimensionless free barrier and RP, and we call here that the RP is a ratio between the vapor pressure and ambient pressure. And we try to define this different atomization process to explore the spray angle and the droplet sizing for some condition. Not for the droplet sizing, we work only for two conditions. Is a work in progress. So to obtain this matrix, we work with one ambient temperature, about 300 Kelvin, and we change ambient pressure between 1 and 7 bar, and we change injection fuel, ammonia, between minus 10 degrees and 50 degrees. So you can observe is the value of RP or the separate degrees. So first step, we study the one spray of ammonia, and we choose to work with injector from engine combustion network, spray M, to facilitate the comparison with the CFD model. And here you can observe the spray of ammonia for isothermal condition, minus 10 degrees Celsius, for different value of RP. And we observe that the spray is very, very thin, and when the RP increase, the angle increase a little. So we follow this value of the angle very near the nozzle, 10 diameter after the nozzle. And if you zoom with the Schlieben setup, we can observe some vapor around the liquid ammonia. So here is plot the mean spray angle very near the nozzle versus RP for different back pressure 1, 2, 3, and 7. And we observe three behavior. First, we observe some dispersion of angle with back pressure. So it's typical of mechanical process. After we observe some increasing of spray angle for the transition behavior in green, one green here, and after the angle is stabilized for the purple green. So we can conclude that with ammonia we have similar behavior. Yes, we can follow these different Lambda criteria to define the angle processes and to help the CFD model to choose the different atomization modelization. So, and if you increase a lot the RP for very high value and for high fuel temperature, it's possible to observe some shock outside the nozzle. For droplet sizing, we do some PDP measurement only for 2 points, and we observe that the diameter of the droplet decrease with increased RP, but it's just 2 points. It's difficult to conclude more about that. So if you study the interaction plume to plume with 7 holes nozzle, is JDI Bosch injector. This nozzle was used to do the experiment, the measurement inside the engine. We can observe that the spray is collapsing, and now the angle is decreased, so the mixing is very, very different than gasoline. So it's for lower temperature, and higher temperature, and for the 2 similar back pressure. So here is an image from Steven technique. So with multi-hole spray, the angle of the spray decrease when increase RP, and we do some measurement of droplet sizing with diffractometer, manual diffractometer for different back pressure condition, and we compare this. We compare the diameter of ammonia with gasoline or ethanol, and we observe that during the mechanical breakup, the diameter of droplets increase, and for flashing mode, we don't observe a very big difference. The diameter of ammonia is very similar of gasoline. So even if we have a flashing mode, the droplet sizing don't change a lot. No, we don't observe a rupture because the temperature can change a lot with the vaporization of ammonia and the high value of latent heat of vaporization. So I have time, so I can show you some results about spray temperature. So I explained that the diameter of the droplet doesn't change a lot, and the reason is perhaps the spray temperature, and we do some measurement with thermocouple inside the spray for different positions, axial and radial, and we observe that in the center of the spray the temperature are very, very low, minus 60 degrees, and in the where there were some liquid and vapor, and after the temperature increase with the mixing of vapor of air, and after in the ambient we reach the high temperature, but the ambient temperature, and this behavior is similar for different RP, and if you measure the lower temperature, this value is, we can find some correlation in function of ambient pressure only. So even if the flash bowling can improve the atomization locally with very low temperature, we can have some condensation effect to increase the droplets. So we identify some different shattering process depending on dimensionless free energy barrier. We observe some that the spray is collapsed from multi-hole nozzles to change a lot the mixing, and there is still a lot of work to be done to study the impact of different conditions in more details. Injection pressure, ambient temperature, as well as the impact of injector geometry. Because there are a lot of phenomena inside the nozzle, so it's important to know the interaction between the fuel and the wall of the nozzle, and the interaction between the different jets. So we need to implement new optical diagnostic to simultaneously measure temperature and droplet sizing, because to quantify heat and mass transfer. So it's possible perhaps to use laser induced fluorescence, laser induced fluorescence to choose a very specific dye to explore at the same time the droplet sizing and the temperature, or use a rainbow spectrometry to determine the reflective index sensitive to the temperature and the diameter of the droplets. So thank you for your attention.
Thank you, Camille. So we have time for questions. You did a very good job in keeping the time. So we can spend some time on questions. First,
okay. So how you measure spray angle in 7-hole injector? Because there are how you measure spray angle? In
just with yes.
Yeah, because so you take all 7 fumes together?
Yes. Here
it
is
is
just global. No, I can't separate the different fume. So it's a global spray.
So you also measured penetration too?
Yes. But
with all fumes?
Yes, and we can observe when if the angle is lower, the penetration is longer.
How you choose at the end boundaries, because there are some. This angle, which angle you took basically? Because there is a spread at end.
I think we use is the last point. Yes.
Okay. No, I'm asking about spray angle boundary.
Yes.
So.
Yes, I measure that
so
here
there is a spread at
okay. So here I measure the spray angle at quarter of spray penetration.
Okay.
So I measure the width of spray here, and I determine the angle.
Okay. Actually, I missed some slides. So what is RP?
RP is is the ratio between the ambient pressure, back pressure, and the vapor pressure in the temperature fuel. So here, the definition is here. Yes, it's the ratio between the vapor pressure in this point and the ambient pressure.
And in one slide, you showed higher basically diameter for ammonia.
Yes.
Yeah. So why it is too high, right?
So for the
one slide.
here.
No. Yeah. Here is okay, but after some slides.
Yes.
Yeah.
Here. So now the back pressure is higher.
Yeah. Why?
Yes. We don't know exactly.
Okay.
But with ammonia, we improve the atomization when the back pressure is very high. Because I think the spray is collapsed, and so they can have big condensation, and some yes, I think there are some condensation phenomena.
Okay, so
because the spray is collapsed.
And some study at higher temperature also or not?
It's not necessary.
Okay.
Yes. Perhaps here, yes, and perhaps we can improve it. Yes, it's difficult to know how it's possible to improve that. Because if you increase the injection, if you increase the injection pressure, perhaps the spray is more collapsing. And but even if the droplet is higher, the temperature after the compression and I'm not it's possible for ammonia to become vapor, even if the droplet is high, and there are no problem of
So
heat
there
with
is
ammonia.
not much impact of droplet size because it is already in
This,
average.
the droplet sizing is sensitive issue for soot.
Yeah.
And with ammonia, it's not the same issue.
Yeah, right. Thank you.
I have a question. I have the right to put a question. I just missed the slide with the temperature measurement, and I wanted to know what was the ambient pressure and temperature.
Here we work. I show the results for this condition. So the ambient pressure is 1 bar, and the ambient temperature is 30 degrees.
And the one which shows minus 60 degrees
Yes.
in the core is the same.
Yes, it's the same.
Okay.
So I measure the temperature for different fuel temperature, and is all these points here. As we measure very low temperature, and when we increase the pressure for this condition and this condition, the temperature increases a little, but it's very low.
Thank you very much. Very nice.
I just saw, in one slide, 7-hole nozzle, your diameter is in micron, and before that, in another slide, you have diameter in millimeter.
Oh, it is micron. It's sorry.
I'm confused.
Yes, it's
this
confusing.
is okay, the previous one.
Yes, it's micrometer.
Yeah, it is.
Yes, micrometer.
Okay, sorry.
We have the diameter is around 16 micrometer,
Okay.
and we have similar value here for similar condition.
Yeah. So I just got confused
yes,
when
yes.
I saw millimeters.
Sorry for this mistake.
Okay. And then you are talking about the results without any contouring, at least whatever results you are presenting, what are the nozzle geometry that you used? Both for 7-hole nozzle and also single-hole nozzle.
Yes.
What kind of geometry of the nozzle?
Here we don't have the diameter of nozzle is we don't have a lot of details about that. We say about the control, and we have and the whole diameter is about 175 micrometer, and for spray M we have more details because it's engine combustion conform with engine combustion network. So we have this geometry of nozzle control here, and the ratio of length of all is about 1, and the diameter is about 170 micrometers. And we have some taper shape. So it's not white, there is a small angle here, in this direction, not this.
Is it specially for this nozzle someter spray injector is specially for ammonia?
No.
It is for.
It's for
all gases?
methanol, gasoline for two.
Okay, it is okay.
Yes.
So it is.
And we like to use GDI injector because we don't have a problem of return of
okay,
fuel.
this is also for GDI.
GDI, because with diesel injector we can have some return, and it's difficult to manage the pressure inside the return because it's not possible to have vapor
So
inside.
nozzle diameter is.
Is
Okay. 170 microns.
yes.
Thank you.
Long live India and France friendship.